Good afternoon, my students. Good morning, good evening. I don't know the time you will be, seeing this class. Like I rightly promised in class, I said we're going to, send a recorded video class to complement what we've done in class so far, and to also help us to have a recorded class that can help us. You can replay this video as many times as you want, pause it at any point you want, jot down some things, clarify some things, and then it makes you understand the topics more better. So this is chemistry 451, chemical process technology. Of course, as you know, it's these 3 units for Abia State University, Uturu, and my name is Professor Engineer JC Igwe. Of course, we're starting with the first module, which is module 1.1, and we're going to be looking at introduction, classification of heat flow processes, heat transfer by conduction, application of one-dimensional heat transfer by conduction, and we'll look at multi-layer flat wall and look at illustrations, and we'll conclude. Introduction. Industrial processes can be widely divided into inorganic, organic processes. That is, all processes will definitely fall into these two major categories. It's either inorganic or organic processes. Inorganic processes include ceramics, glass, cement, metallurgy, which I know you do courses in this area also. And organic processes include lipids and detergents, heavy chemicals, fine and specialty chemicals, petrochemicals, plastics and polymer, drugs and dye stuff, and so on. Physical operations in widely different industries are similar. These operations were seen to be similar, and because of that, we'll have to find a way of bringing them under one umbrella so it becomes easy for us to study all of them at the same time. So this is the concept of unit operations. That is reducing every operation in terms of one or more already established operational steps. That's what we call unit operations. It gave rise to unit operations. Now, unit operations includes evaporation, distillation, there are so many of them, sedimentation, and so on. And these are facilitated, a variety of process units and equipment are facilitated by occurrence of transport of momentum. Of course, we will see later look at momentum transport, or fluid flow, heat or mass, or combinations of the two or all three occurring simultaneously. For example, extraction and gas absorption involves mass transfer, while distillation and humidification involves heat and mass transfer. Therefore, this means that all operations develop a more fundamental phenomenon, namely fluid flow, momentum, mass, and heat transfer. These rates of transfer processes of momentum, heat, and mass are collectively known as transport phenomena. So we're going to discuss the basic principles, the applications, and equipment. Classification of heat flow processes. Heat can be transferred by conduction, convection, and radiation. Conduction takes place through a medium, but there is no bulk movement or translation of the molecules. The molecules merely oscillate within very minute distances comparable to molecular diameters. So in conduction, there is no bulk motion. There is no flow. There is no flow of the molecules from one place to the other. That's what I mean by bulk motion. And it needs a medium. It's just like when you're heating an iron and you're holding one end. What happens is that the molecules close to where the flame is picks up energy and start vibrating, transfer their energy to the nearest molecule, That other molecule, the temperature increases, transfer to the next molecule, and it continues that way until it gets to the end where you're holding it. And that's why if you don't have an insulator, you're not holding it with an insulator, then you feel the heat or you feel the hotness of that rod you're holding. Now, but in convection, heat flows by actual mixing of warmer portions with cooler portion of the same material. Convection also takes place through a medium, just like conduction, but there is bulk motion. So you can see for conduction, we need a medium, but there is no bulk motion. But convection, we also need a medium, but it has bulk motion. Convection arises due to eddy currents set up by changes in density with temperature. If you look at boiling water, the molecules of water close to the flame picks up energy from the flame, from the heat, and there will be increase in kinetic energy. And of course, because of increase in temperature, the density will reduce, and then the molecule becomes less dense and will now travel up to replace the molecules up, and the ones up will be more dense, will come down, and that cycle, as it is happening, will now see the movement, and that's what we call eddy currents. And these eddy currents are set up because of changes of density with temperature. Radiation is the transfer of energy through space by means of electromagnetic waves. Radiation does not need a medium. Radiation is not transferred into heat in empty space, but when it comes in contact with matter, it is transmitted, reflected, or absorbed. And of course, the radiation is simply visualized from the radiative heat of the sun. The sun's rays gets to us through radiation, radiative transfer. In all these heat transfer processes, the transfer of heat is occasioned by the existence of driving force, which is a temperature gradient, a temperature difference over a distance. So once there is a temperature gradient, the two bodies at different temperatures will want to equilibrate, and that will make the transfer of heat. In most cases, combinations of 2 or 3 modes of heat transfer occur simultaneously. Heat transfer by conductor. Now, we want to just look at conduction. We mentioned conduction, convection, and radiation. And heat transfer by conduction is best illustrated using solids. And the equation for heat transfer is what we call the Fourier equation. This is given by equation 1. The quantity of heat divided by area, which is the flux, is equal to K delta T divided by delta X. The T is the temperature gradient, the X is the distance. Now the temperature gradient is negative, hence the negative in sign in that equation 1, which takes care of that negative in the temperature gradient. Of course, Q, small qx is a flux because we have quantity over time over area. Remember, Q, capital Qx is the heat, rate of heat, that is the quantity of heat over time. If you divide it again by area, it becomes a flux. So if we integrate equation 1, we will get equation 3. And that gives us, if we rearrange, we'll get equation 5. And that gives us a form of rate is equal to potential difference over resistance. So it means that the heat flow through by conduction is directly proportional to the thickness but inversely proportional to the thermal conductivity and the area. Now, for multi-layer flat wall, that is when we have 2, 3, 4, or even more flat walls put together. The heat has to pass through each of those walls. We have just examined heat conduction through a flat wall or slab. Now the Fourier equation has been presented, If the heat is flowing normal to the principal surfaces, the area term A is constant. If the conductivity is assumed constant, then Q at any cross section is proportional to temperature gradient. Now we have to apply one-dimensional heat transfer by conduction. So if energy is neither generated nor accumulated in the wall, Q is identical at all cross section. But in many industrial processes, it is necessary to keep heat in or out of the system by providing insulation. So if you have a cold room, you don't want the cold room to be heated up. If you have a furnace, you don't want it to cool down. So there must be some kind of insulation to maintain the heat in that system. So now we examine composite bodies. Look at the composite body. We have three here: delta X1, delta X2, delta X3. And then we have T1, T2, T3, and T4. Now this is a multi-layer flat wall that you're seeing. For steady state, Q is the same across the wall. So that equation we had before, Q is equal to K1A, T1 minus T2 over the X1. That is for the first wall. Is also equal to K2A, T2 minus T3 over the X2 as for the second wall, and is equal to K3A, T3 minus T4 divided by the X3 for the third wall. Now if we divide all through by area, which gives us a small q, to give us that equation, therefore T1 minus T2 is equal to Q1 dx1 over K1, T2 minus T3, the same thing, and then the overall, which is T1 minus T4, will now be, because our Q, Q1, Q2, Q3 is the same, we now have a Q overall in brackets dx1 over K1 plus dx2 over K2 plus dx3 over K3. Therefore, our Q overall is written as that. So we can use this to calculate the heat flow or even a thickness of any particular body that we need to calculate. Okay, fine. An example, an illustration, the first one, we are given, we have two materials, so we have two components, dx1 and dx2 and k1 and k2. So just take your time, look at that as is already solved. The same thing, illustration 2 is also solved, but in this case we have three, dx1, dx2 and dx3, and we also require to find the temperature at the interface. Okay, in conclusion, we've looked at classification of heat flow processes, heat transfer by conduction, application of one-dimensional heat transfer by conduction to multi-layer flat wall. And I believe that when you look at those illustrations very well, you will understand these principles more. Thank you very much, and see you in the next class.